Hi, my name is Shahnawaz. In this lecture, we are going to study the fundamental groups. We start this lecture with the following definition, i.e., the definition of a loop. So far we have seen that a path in a topological space X is actually a continuous map from a closed interval I into X. So let us consider a path, say F. Let F be a path in X. So note that here I is the unit interval, closed unit interval 0 1. So this path is in X such that the add points are identified, that is f of 0 is same as f of 1, and let us give them a common name, say x naught. Then this kind of path is called a path, then such a path is called a loop. Then we call f a loop. This point x naught is called the base point of the loop. So the common initial and final point, initial and final point. This x naught, this is referred to as the base point. This is referred to as the base point. Let us write this base point as a single term. So suppose this space X is given as suppose this space has a hole here, say this is the hole in the space. Now let us consider a path. Suppose this is a path with common initial and final point. So this is the base points. Let us name this point as x naught. So this is a loop in space X. So similarly we can draw a loop here around this hole. So suppose this is the base point here. Let us draw a loop here. First of all, we'll make some remarks here. So this is remark first. We know that the relation of homotopy on the set of all paths with a fixed endpointers in any space X is an equivalence relation. So this means that the equivalence class of a path F under the homotopy relation is called the homotopy class of F, and is denoted by, suppose we know that the relation of homotopy on the set of all paths. With fixed pointers, with fixed end pointers. In any space X is an equivalent solution. So this is the equivalent solution, and the equivalence class of a path F under this relation is called the homotopy class of that path. The equivalence class of a path F so of a path F under this relation, I mean the homotopy relation, is called the homotopy class of F. And it is denoted by F with these square brackets. So this homotopy class of F, it contains all those paths in X which are homotopic to G F. So if we consider, suppose this is path F here, now the homotopy class of F is all these loops here. So this is the homotopy class of F, all these loops here. Of course they are infinitely many. Similarly, the homotopy class of this path, suppose this is path G, so it consists of these loops around this hole. Now let us make another remark here. So we have proved that the product of homotopic paths is homotopic, that is, so we know that if, say, F is homotopic to G and F prime is homotopic to G prime. So now these paths are homotopic to each other, so their product, that will be also homotopic. So their product will be also homotopic. So we know that if this is true, then product of F with F prime, sorry, this is F prime here, this is homotopic to product of G and G prime. So this means, this will imply that this product operation, that has to respect the homotopy classes as well. So this will imply that this product operation it has to respect the product of homotopy classes as well. This also respects the product of homotopy classes. This respect is the homotopy classes as well. So this means that if we product two, suppose if we have two homotopy classes G, then their product is defined as this is equal to the product of equivalence class of the product of F and G. So note that this F and G, product of F and product of G, this is, so this contains, so it contains an element here and an element here. So this is say F prime dot G prime, such that F prime is in F and G prime is in G. That means it consists of all those paths, this F prime G prime, such that, so since F prime dot G prime, this is homotopic to F dot G, so this is such that F prime dot G prime is homotopic to F dot G. So this is same as the homotopy class of F prime dot G prime. So one can see over here, so this homotopy class over here, which is a homotopy class of F, and this, suppose this is a homotopy class of G. So these two classes, they are not equal. The reason being F and G, they are not homotopic. Now why F and G are not homotopic? It is because all these loops over here, we can pull all these loops all back, all down to this point x naught here. However, if we pull these loops, they are gonna get caught at this hole. So beyond this hole, beyond this stage, we cannot contract these loops further because they are gonna get caught near this hole. So what I'm actually trying to say is that, suppose we have a surface like this. Now this surface has, say, some hole here. So if we have a loop here, this loop is actually, since this loop F, since we can contract this loop to this point, say this is point x naught, so we can say that this loop F is homotopic to the constant loop Cx naught, which is actually x naught. However, if we have a loop here around this neck here, around this hole here, say this is the loop G. So this loop G, we cannot contract this loop all back down to this point, because this loop is gonna get caught near this hole. So these two loops, they cannot be homotopic. We cannot deform one loop into another. So let us make another remark here. So let us consider a loop with base point x naught. So let f be a loop in x, be a loop in x with base point x naught, which is some point in x. Then the set of all maps, so then the set of all maps in x, that is G is in CIX, such that f is homotopic to G, will give us the homotopy class of f. So this is the homotopy class of f. Now let us fix some notation here. That is the set of all distinct homotopy classes. Distinct homotopy classes say f. So these homotopy classes are the classes of loops. So f is a loop from I into x at base point say x naught is denoted by pi of x with x naught. That means this set pi of x naught, this is the set of all homotopy class f, such that this f is a loop with base point x, such that f is a loop in x with base point x. Say x naught. Now this is up to homotopy. So let us take this quotient with the homotopy. So these are homotopic. Suppose if we have f and g such that there are two loops which are homotopic to each other, so they will give us only one class. So that means they are up to homotopy. That means these elements here, they are not, these classes here, they are not homotopic. So what does that mean? Say we have a surface here, suppose this is point x naught. Now suppose we have these loops. So So this is the class F. So this is the class of F. Now let us take another class here. So this is the class G. Suppose this is the map G, this is the map F here. Since F and G are since these F and G they are homotopic, so F is homotopic to G. This means that these two classes they are equal. So this is only one element here, because these classes are these classes are homotopic to each other. However, suppose we have a hole here, and let us, so this is the hole here. Now let us take this class here. So suppose is the class of H. Now note that if this is the map H here, since H and F they are not homotopic, since H is not homotopic to F, so their classes, homotopy classes, will be distinct. So these two elements will give us here these two classes. So one should understand the meaning of this quotient here. So these elements here they are up to homotopic. So we are going to prove an important proposition. So let us do the following proposition. So this proposition states that suppose we have suppose this set X with X naught. So this is the set of all loops or let us do this way. So pi of X naught is a group with respect to the group operation so here we have to define a group operation with respect to group operation F dot G, that is the homotopy class of F dot G. So this is the operation. This operation is called the product operation with respect to a group operation given like this. So we have to prove that this is a group with respect to this operation. So first of all, we will show that this operation is well defined. So next in next lecture we'll prove that this proposition, that this pi 1 of x naught, this is a group.